All right. So it says, what is the final velocity of an object that has been shot out of a cannon with horizontal velocity right here? What is the final velocity of an object that has been shot out of a cannon with a horizontal velocity component of 18 meters per second and a vertical component of 21 meters per second? The object lands 2.0 meters above the point of launch and 70.0 meters away, right? That's what it says.
Yeah.
Yeah. So first thing we'll start with is a diagram. Now it doesn't say that the object has been shot from any height, so we assume it's from ground level. Okay. So we assume your cannon is right here. Right. Not good at drawing, but your cannon, let's assume, is right there. And okay, that's good enough. And you shot, it says, what is the final velocity of an object that has been shot out of a cannon with a horizontal velocity component of 18 meters per second and a vertical component? Okay, so cannon is shot, it follows a parabolic trajectory, and then it lands 2 meters above the point of launch, assuming the launch is at ground level. It lands on a net up here, right? Lands 2 meters above the point of launch. So let's pretend that right there is 2 meters. Right there. Okay. That's your 2.0 meters right there. It's right there. Clear. Let's just write. That's your 2 meters. So it is shot from there and it lands right there. All right.
Yeah.
Okay. So I hope you do that diagram. And so we want to know the final velocity. Well, first of all, the initial velocity is right here. Let's go to a different color. That's the initial velocity. That is the initial velocity in the x direction. That is the initial velocity in the y direction. Okay?
Yeah.
Now it's a vector quantity, so you can write arrows on top. I will leave them out for now, but you can write them. So that's your initial velocity in the y direction. Now, it has a horizontal velocity component of 18 meters per second. So that Vix is 18, initial velocity in the x direction. That's your 18. And the initial velocity in the y direction is 21, so vertical component, that's upward 21 meters per second, that magnitude. And we have that right here, 2.0. Now, it started from ground level. So at ground level, your initial y is 0 because it's at a height of 0. It started from a height of 0. But it lands up here. So your final, it lands up there. But the initial point of launch is ground level. We don't consider it from here. We'll say that height is negligible. So technically, it started there. Understand?
Yeah.
And that, unless they gave us additional information and they said that at the chute of the CHUTE chute of the cannon was, maybe certain number of meters above ground level, then we would consider that height as our initial Y. But we had no such information, so we assume that height is negligible, and we start with initial Y equals to 0, just to be clear. And sorry, I meant the final Y now. That was the initial Y is 0. Now for the final Y, right there, that's going to be 2.0 meters above ground. So that's 2.0 meters. And that's important because delta Y is always final Y minus initial Y. So in this case, it's going to be 2.0 minus 0 because final is 2.0. So that's going to be 2.0 meters minus 0 meters. So that's going to be 2.0 meters. Or using common sense, if the landing is above the launch point, then delta Y will always be positive. If the landing is below the launch point, delta Y should always be negative. All right?
Yeah.
So that should just be logic, common sense. Okay. So in this case, since my landing is above the launch point, then delta Y is positive 2.0, and it's positive 2.0 is because final minus initial 2.0 minus 0 is positive 2.0. Now, so that takes care of that. It also told us that it launches, it lands 70.0 meters away from the launch point. So what they're also telling us is that this distance from here to here is 70.0 meters. Right there. And that will be your delta x. So they're telling us that delta x is equal to 70.0 meters. That's the displacement in the x direction. Got it?
Yeah.
Okay. So I'll use everything in the horizontal direction represented with an x, and everything in the vertical direction I'll represent with a y. Now, the question asked for the final velocity. So the final velocity vector will be downward. Let's use black again. Will be this way. So to get to that final velocity vector, that means we'll have in the vertical direction, the y component of that vector will be downward, and the horizontal component will be to the right. Make sense?
Yeah.
Okay. So that's your final velocity in the y direction, and this is your final velocity in the x direction. Now what we know is that everything in the x direction, so let's write down what we know. So x for the x direction, and let's write down everything we know for the y direction. So in the x direction, for these projectile motion problems, the acceleration in the x direction is always 0. It's never accelerating in the x direction. In the y direction, depending on which planet we're on, and we're talking about Earth here, so therefore acceleration is going to be negative 9.8 meters per second squared. Negative because it's downward. Okay, so again, vector quantity, so you can write an arrow, but if I don't, just still know that it's a vector quantity. Okay?
Yeah.
So acceleration in the y direction is equal to negative 9.8 meters per second squared. And that's because gravity, acceleration due to gravity on Earth. If we were talking about launching something on the moon, then everything, well, all the laws of physics in the universe, in the entire universe, should be consistent as far as we know. In this case, the only thing that would be different is gravity. So if we were on the moon, then that would have been like negative 1.6 meters per second squared, for example. So things with that value would be different. Okay. So since the acceleration in the x direction is 0, that means the initial, if there's no acceleration, then velocity is constant. And if velocity is constant, that means the initial velocity in the x direction will always equal to the final velocity in the x direction. So we can just go ahead and say velocity in the x direction instead of writing Vix and Vfx. So therefore, what that means is, and I don't know what happened to my diagram, but it got deleted there. So let me draw that again, that tangent again. So final velocity is just the velocity right before it hits the ground. So again, that's downward and to the right. That's my Vf. This is my Vf in the y direction. And this is my Vf in the x direction. So we know Vf in the x direction will still be the same as the Vx in the Vi in the x direction, which is 18 meters per second. Do you see?
Yeah.
So therefore, Vx we know is always going to be 18 meters per second. Right there, 18. Don't know if I have space to write everything down. But the Vfy we don't know yet. Got it?
Yeah.
And we don't know what Vf is either. That is what we're trying to find. So what we're trying to find is this Vf though, not this Vfy. That we need to find that in order to find Vf, but our requirement is to determine Vf, the final velocity. It didn't say what is the final velocity in the y direction, in the vertical direction. It just said what is the final velocity. So this is the one that we want. But we need to find this one in order to find that one. Okay. Of course, this is also a right triangle right there. All right. So what else? Have we written down everything we know? All the given information? Not yet. So we know that delta y, we do know that since acceleration is not 0 in the y direction, we know that the initial velocity in the y direction does not equal to the final velocity in the y direction. Those are different, right?
Yeah.
If I'm not going to write arrows, then I'll just be consistent in not writing arrows. So VIY, the initial velocity in the y direction will not equal to the final velocity in the y direction because acceleration is not 0. Because acceleration in the y direction does not equal 0. Okay. But over here, they are equal because acceleration is 0. Okay. And we also know that delta y here, we already figured that out underneath the diagram, was positive 2.0 meters. We already spoke about that. And we know that delta x is 70.0 meters. Now, the first kinematic equation that we're going to pay attention to is delta d equals to initial velocity times delta t, or I'll just write t, minus half times, or rather plus half times the acceleration times delta t squared, or t squared. So focusing on that, right here, the reason why this equation is always delta x is just Vx times delta t is because acceleration in the x direction is 0. So if a is 0, then this term right here disappears, and you're just left with delta d equals to Vi t, delta t. So that means that's the only reason why delta x in the x direction is always going to be the equation where it's just initial velocity in the x direction, or in this case, initial velocity, final velocity are the same. So we're just calling it velocity in the x direction times delta t. Understand?
Yeah.
So if you wondered why is it always that equation, well, that's because based on this kinematic equation right here, since acceleration in the x direction is always 0, well, then that we don't have this term and we're just left with that. Okay. And over here, however, since acceleration is not zero, we're going to have delta y equals the initial velocity in the y direction. Everything is in the y times delta t plus half times acceleration in the y direction, which is just g, times delta t squared. Okay. Now, let's plug in what we do know. We do know that this delta x is 70 meters right there. I won't write the units right now, so don't take up that much space, but we know delta x is 70 meters, and we know Vx is 18 meters per second, so 18. And so we can easily solve for t. So t is 70 divided by 18. Do you see?
Yeah.
Okay. Now, do we even need t? We'll see, but who cares? It's easy to solve for. So just in case, at least we have that out of the way. So it was easy, so let's just do it anyway and get it out of the way. 70 out of 7, what's 70 divided by 18? I mean, so that should be 3 point something. What do we have? 18 times 4 is 72, so 70 over 18 would be what? 27, so 3.8888, so 3.89, is that correct?
Yes. That's what I got before too.
Yeah, 3.89 seconds. I'm just doing it in my head because anything divided by 9, for example, 1 divided by 9 is always 0.111111, 2 divided by 9 is 0.2222, 0.5 divided by 5 divided by 9 is 0.555. So in my mind, I was just about 70 over 18 is 35 over 9. 9 times 3 is 27, so the whole number is 3. And then difference between 27 and 35 is 8, so 8 over 9 is 0.88888, which means rounds to 3.89. So delta y is equal to vi yt plus half ay delta t squared. All right, so now delta y I already know. So again, I'll leave the units out in order to save space. And so 2.0, but if you need to write it, you make sure you do it on your test. So 2 meters, and initial velocity in the y direction, well, what was that? Oh, wait a minute, now I have all the information, so left side will just equal to right side. So I don't even need to use that equation. I don't need to use that equation because what I need to do is find the final velocity in the y direction. So the kinematic equation that I'm interested in using is based on the information I have, is the final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration in the y direction. Well, we'll get to that, but I mean, the general kinematic equation is what I meant to write is final velocity squared equals initial velocity squared plus 2 times the acceleration times delta d, right? You're familiar with that kinematic equation as well.
Yes.
Okay, so that's the one I want to use to find the final velocity in the y direction. Now, having said that, could I also use this one? Absolutely. Could I also use this one, the final velocity equals initial velocity plus acceleration times time? Sure, because I figured out the time, so I could, right?
Yeah.
But suppose you didn't find the time, then obviously the ideal one to use would be that Vf squared equals to Vi squared plus 2AD. So you have options, but just stick with that one. So final velocity in the y direction squared equals initial velocity in the y direction squared plus 2 times acceleration in the y direction times delta y because it's in the y direction. So what we're trying to find is this final velocity in the y direction. And right now it's squared equals to the initial velocity in the y direction. Well, I believe that was 21 meters per second, right? I didn't write that down in the given information. 21 meters per second, right? Do you see that?
Yep.
Vertical component of 21 meters per second. So therefore, we have final velocity in the y direction squared equals initial velocity in the y direction was 21, so that's 21 squared, plus 2 times acceleration in the y direction, negative 9.8 here on Earth, and delta y was 2.0. Now, when we solve, because we are dealing with vectors, even though I'm not writing arrows, as I said a million times now. So keep in mind, we should get a negative answer for VFY. Well, we're taking the square root, so right now we're just finding the magnitude, but the direction is downwards. Do you see? However, when we solve for it, yeah, we should get the positive value because we're going to be taking the square root. So now we have VFY squared equals to 21 squared. I know that's 441. That's easy. Positive times negative, that's going to be negative. 2 times 9.8 is 19.6 times another 2, 39.2. So obviously we should get a positive value here, otherwise we won't be able to take the square root. So what's 441 minus 39.2?
Minus 39.2. I got 401.8.
Mm-hmm. And now I'm going to need the square root of that. So that should be 20 point something.
Yeah, I got 20.0449. How many decimal places are we keeping?
Like I said, whatever is required in the final answer, the number of significant digits, you should keep at least one more in your steps. This is not the final answer yet.
Right. Okay, let's do 20.045.
Mm-hmm. That's at least one more, but that's still too many. So let's just say 20.0 is perfectly fine.
Okay.
20.04 you said?
Yeah.
Okay, so 20.0 is fine because I believe the final answer requires 2. So
Yep.
we keep at least one more. So we have 3. They're good. Now,
Sir,
um,
I have a,
yeah, 1 second. So
okay.
first of all, technically this is supposed to be plus or minus when you take square root, right? Because technically it is, like I said, a vector quantity. However, then you communicate that it's going to be negative 220.0 because it's downward. Understand?
Yeah.
So that means the positive one is inadmissible. Yeah, go ahead.
Yeah, so when I use the equation v final equals v initial plus acceleration times time, when I use that equation instead to find our final velocity in the y direction, I got a different answer, and I'm wondering why.
You use 3.89 as time.
Yes, I use 3.89, but I've because of school, I've always been in the habit of using negative 9.81 meters per second squared as the acceleration.
Okay, well,
Uh,
you should have told me that because that's true. Some teachers use 9.8 and some teachers use 9.81. But you should tell me ahead of time what you use. Now, if I'm looking at the answers in this textbook, they use 9.8. So to get accurate answers from this textbook, we'll stick with 9.8.
okay.
Some textbooks use 9.8, some textbooks use 9.81. So just to make sure that our answers aren't off, that our answers are accurate. If your school textbook uses 9.81, great, but majority of the textbooks, they do use 9.8, though 9.81 is more accurate. However, having said that, still, majority of the textbooks still use 9.8. So therefore,
Okay.
if we're checking the answers from this particular book, then just for accuracy, we're going to stick with 9.8.
Okay. the formula I was talking about, I got negative 17.122 meters per
Okay,
second.
I will check myself.
I'm wondering why I did
So
that.
21 plus, or rather minus, because yeah, you're right. You get negative 17.122.
Yeah, that's what I got for the final velocity using that equation. Why did we get something different when we used this equation?
Yeah, so I think the first one is more accurate because the second one doesn't take into account, because we're talking about the y direction. The second one doesn't. The first this one that we just used doesn't take into account the delta y that it launched 2 meters above ground level. That's why.
Okay.
So therefore, we shouldn't use that one. Had we not known what delta y is, then it'd be a different story.
I see.
Then it shouldn't have made a difference. But yeah, so we won't worry about that one. So that's why. All right, so getting back to this, we're going to use the negative 20. And now we need to find that VF. So now we can just use Pythagorean theorem to find the VF there. So it's going to be the square root of 18 squared plus what we found. So the final velocity, and we're only talking about the magnitude part. You know what? Yeah, let's go ahead and include the arrows when it's vector. And so therefore for magnitude, we don't have to use the absolute value bracket. We'll just do it without the arrows. So that's going to be the square root of 18 squared plus 20 squared. So let's just work that out. That's 324 plus 400. 18 squared is 324. 20 squared is 400. That's 700. Well, it's still approximate because that 20 was rounded, so that's fine. So what's the square root of 724?
24.
So if you check, that's 26.9, which now if you round to correct to two significant digits, is what the book said, which is 27. Do you see?
Right.
Is the answer I said it would be, should be.
Yeah, I got something different because I used the other formula that you erased. So in that case, how would we know which formula is more accurate in
So
that
I
case?
told you that was my mistake, and I already explained that. I said because that doesn't end, because we knew what delta y was, and in
Yeah.
that formula we don't take that into account. I don't have another explanation for you. That's
Okay.
why. So I already explained that.
Okay.
All right.
Yeah.
So yeah. So that was already asked and answered. Okay. So that's 27. And now for the angle, we'll go back here. And we need to find that is, well, no, sorry, not that angle. It is this angle that we need to find. All right. So to find that angle, we'll just do the magnitude of the final velocity in the x direction divided by the magnitude of the final velocity in the y direction. So that's going to be 18. And this was 20, so 18 over 20. And just do that up here. So see that tangent theta is going to be 18 over 20. And what does that give us? What's the inverse tangent of 18 over 20?
I got 42 degrees, and this is rounded to 2
So 42 degrees approximately. So that means you can write your answer two different ways, as you can write your direction in two different ways, as down 42 degrees right, or you recognize that there is a horizontal there, and the complement of 42 degrees is 48, because 42 plus 48 makes it 90. So if that's 48, then another way to write it is right 48 degrees down. So the answer in the book is right 48 degrees down, but our answer of down 42 degrees right is the same thing. Do you understand?
Yeah.
As right 48 degrees down. So you can write your answer. The direction, as I explained last time as well, can be written in multiple ways. So therefore, the final answer is 27 meters per second. And you could say down 42 degrees right, or as I said, you could say right 48 degrees down, and they mean